Diganta, I suggest we wait for 5 minutes.
Yeah, sure. Works for me.
Yeah, let's see. So there are 5 people now. So I don't know.
Addition.
I think you should start, Diganta. But yeah, before you start, I want to
Yeah, okay.
know that today we have only a basic version, so we can only go up for per session only 40 minutes. So after 40 minutes, I might have to restart. Okay, I will have to restart another session. Yeah. Um,
Okay, okay, sure.
and people have to rejoin after I start. From next time onwards, I'll make sure that I have procured a full a license, a professional license. I had to give some prior notice, and today I did, and it was too late. I mean, we could try uh, I could try ending this meeting and again starting, and I don't know if that will help. Shall we do that, or shall we continue with this in at 40 minutes? Um,
I mean, either way is fine with me. Whatever everybody else prefers is okay with me.
let's see. So there are one, two, three, four. Only four people. Uh, just one person dropped off. I don't know who. Okay, I mean you have to. Yeah, let's start. Okay, and I'll make you a co-host so you can share.
Okay. Yeah, so I'll start sharing my screen. Okay, so yeah, so last time we had talked about again we completed this brief introduction to machine learning, and what we had talked about last thing that the last thing that we discussed was this idea that we are going to, this question, how are we going to optimize L theta, right? And the way that we're going to do it is via gradient descent. So if you remember what machine learning, I mean, just a brief recap, what the idea was that we had some data and now we wanted to somehow find a function that is trained well on this data. And what we say is that, okay, this function is going to be really be a parameterized function approximator. So instead of finding the function, what suffices is to find the value of these parameters. And how are we going to find the value of these parameters? We're going to optimize some loss function, which we're going to use the data to define. And once we've defined this loss function, we're going to optimize this loss function via gradient descent. And once the gradient descent has run its course, it's going to give us a value of theta that should work well, at least on the particular dataset that we have, and we hope more generally beyond the dataset as well, right? So this is kind of the crux of what we discussed last time, and the major thing that I kind of very briefly skimmed over, which I felt I should perhaps spend a bit more time on, is how do we actually, an important part of this gradient descent step is to actually calculate the gradient of this loss function L theta with respect to theta, right? And if you remember from last time, we had done this kind of setup for this digit classification example, this MNIST example. So by the way, this digit classification data set is called the MNIST data set. And this is a fairly complicated example, right? I mean, the loss function has got so many pieces to it. It's got these PIs, which are again going to come from the neural network. The neural network itself is this huge expression involving so many layers and so forth, right? So how do you calculate this, uh, this kind of a gradient very nicely, right? So is there a nice way of doing it? Turns out that there is actually a very nice way of doing it, and that is the first thing that I'm going to talk about today. So that should not take too much time, but I'm going to talk about that in some level of detail, and it's going to tie in very well with the PyTorch tutorial that is probably going to happen sometime soon. And after that, I'm going to move on to talking generally about why we want to use formal methods in neural network. and applied to neural network for understanding the trustworthiness and safety and explaining neural networks and sort of motivate neural network verification as a field, right? So this is going to be the next this lecture and maybe some of the next lecture. First, some background about this calculating the gradient, and then talking about some motivation behind why we want to do formal analysis of neural networks at all. Okay. So before I start, is there any questions from last time or any questions about the setup or anything? Okay. So, right. So let's talk about backpropagation, right? Okay. So suppose, so what I'm going to do to introduce backpropagation is I'm going to take a function on these two variables a and b, and I'm going to ask the question: how do we efficiently compute the gradients of this function with respect to its inputs? In this case, the inputs are a and b. So we want to compute del y del a and del y del b, right? And remember, we don't want to do it generally. We really only want to do it for some certain kinds of points, right? I mean, if you go back to the gradient descent algorithm, the we only really care about the gradient at each of the points over here. So whenever we are at a certain point, which means whenever we have certain values of our parameters, which means whenever we have certain values of our inputs to our function, we just want to calculate the gradient at that input, right? So we are only really interested in calculating this at some particular theta, right? So how do we do that efficiently, right? Or why is this even? I mean, how hard is of a problem is this? How do we do this efficiently and so on, right? So let's look at the firstly the kind of maybe naive way of doing it. So to look at that first, what I'm going to do is I'm going to introduce a bunch of new symbols, and I'm going to draw out what is known as the computation graph of this function. This is not really needed to calculate a partial derivative. You can just take del y del a and just expand it out using your various rules. But just doing this is going to help me explain and talk about things a bit better. And later on, it's going to become key in introducing the kind of backpropagation algorithm that I'm going to so that I'm going to talk about, right? Okay, so we have this function y is ab plus a sine pi ab, right? And there are various these kinds of pieces. There's ab, there's a, right? This sine of something going on, and so on, right? So what we can do is we can think of this function as computing this particular value as doing so on a DAG, right? Where each node of this DAG is going to compute some kind of a sub function. So let's say that we firstly take u equal to ab. So we firstly calculate this product ab and we store it in some intermediate variable. Let's call it u. And then we take v is equal to sine of u. By the way, this is readable, right? Like, can you guys read this, or is this too small? Is my is the handwriting and all okay?
I
Maybe I
think
should.
it's fine for me. I
Okay,
can
sure.
read it. So,
Yeah, yeah, yeah. Maybe I should not have. Yeah. So anyway, so this is these are all of the various intermediate variables, and let's complete this diagram now, right? So we have now a times sine pi ab, right? So in fact, I'm going to modify this to say something like, let's say, pi of u, just to make it a bit easier when we do the calculations, right? And then we want to finally calculate a times this, so we have another w, which is going to be a times sine or a times v, let's say, right? And then finally, my output is going to be the sum of these two things. So we have y is equal to u plus w, right? And then we can calculate del y del a in this kind of standard process, right? So we can say um, that del y del a is going to be del of u plus w, right? So a, which is del u del a plus del w del a, right? which is now what is del u del a? Del u del a is going to be del ab del a plus del w del a is going to be del av del a, which is uh, so okay, and this is all at 2 comma 3, right? So if we do this now, then del ab del a simplifies to something like b, plus this guy simplifies to v del a plus a del v del a, and this guy now becomes b plus v plus del v del a is again going to be something like, so it's going to be, remember, this is at this particular value 2 and 3, so this is going to be uh, cos pi u del u del a, but then u at 2 and 3 is simply 6, so this guy becomes 1, so that simplifies to just saying del u del a, or yeah, so actually there should be a pi here, plus again the del u del a we have calculated before, but we'll have to do it again. So this is going to be b plus v plus, I'm not going to repeat all that, all the working out, but basically again we get b pi b, right? And then finally we can plug in the values of b and so forth to get some kind of an output, right? So this is the whole calculation you need to do for to calculate the gradient, right? And then you have to repeat this again for del y del b and so forth, and this feels like a lot of computation, right? So, and remember that we'll have to do it again and again for various different kinds of points. And the question is this, how much time is this going to take, and is this going to take too much time, and maybe can we do better, right? So the first question that we want to ask is how much time is this going to take, right? So notice what we're doing here is we are starting with the kind of the bottom level, and kind of one way to think about what we're doing is kind of starting with the bottom level and going up, right? When you think about this b plus v plus pi del u del a, so what you're really calculating over here is, okay, you're calculating here the gradient of this guy with respect to a. And then you can say that, okay, and now I'm going to next calculate the gradient of this guy with respect to a based on these two gradients, right? And going to keep building up and so forth. And finally, we'll have the final output over here, right? But if you do this, notice that for each computation that you're having to do, you're having to, sort of calculate the gradient all over again, right? So, for example, this AB, we had to calculate the gradient kind of twice, right? So once when we were going by this path, and we had to calculate the gradient here. And then when we simplified this expression, we find that, okay, V was simply this guy. So del V del A, we had to calculate again, right? So immediately we should notice that, okay, we are actually you know sorry, del u del v, we have to calculate again, right? So we're actually doing some kind of a repeated calculation in this naive expansion of this expression, right? So maybe we can memorize some of those, and gain some speed up, correct? And also, another interesting question to ask is that when we now calculate del y del b, do we have to do this whole thing again? Is there some repeated calculation that we can take care of? See, one of the things that's happening when we're calculating these expressions, for example, when we calculate del w del a, the way that we're expanding del w del a is saying that we're saying that, okay, w is really just av, and we're saying that, okay, let's take del a del v del a del a, and then substitute those guys back in, right? So is this kind of a is this kind of repeated calculations, can they be reused somehow, right? So these are the few questions that we want to understand and answer. So to concretize these questions a bit more, what I think is a good idea is to um, say what this kind of a framework, this a differentiation, a framework that calculates the derivative needs to be able to do, right? So generally speaking, you're going to have some computation graph, and you're going to have various expressions here that look something like this. Some intermediate variable is equal to some function of your values, right? And then I have got another intermediate variable equal to some new function g of, let's say, these two guys, right? Uh, some, a, b, maybe u as well. And then finally, my output is just, let's say, this v, right? So if I want to calculate del V, del A, right, this is going to involve calculating, okay, that is basically calculating del G of A, B, U, del A, which is going to be, okay, what is so notice that for any given particular function g, what we can kind of know, or what we can sort of think of as a rule, is what is the derivative of del g at various values of its inputs, right? So for example, for sine, we know that derivative of sine x with respect to x is going to be just cos of x, right? If this x is a more complicated expression, we don't know what we need to do, but at least we can know this much, right? So what we know about g is essentially, we know that del g, del a is going to be something, del g, del b is going to be something, and so on and so forth, right? So we can immediately write this as something like del g, del a plus del g, del b plus del g, del u. And then we need to find whatever del u, del a is, right? And similarly, del b, del a, correct? Now, if we do, so this is essentially what we're doing in this naive expansion, right? So these values are something that that given our kind of these atomic subfunctions we already know, but these values we have to keep expanding. And what we're finding is that when we keep expanding these kinds of things, there's a lot of common computation that we can, that we should be able to take common and avoid repeating, right? And this is kind of the key idea behind this backpropagation algorithm, which is to say that, look, these common computations that you want to avoid, these are precisely going to be these kinds of gradient calculations within the computation graph, right? So what does that look like? Let's go back to our example. Maybe I should just duplicate this guy. Yeah. Yeah. So if you go back to this graph, notice here that when we want to calculate del y, del a, right? We know that, okay, this is going to be, so y is just a function of u and w, right? So y is some function of u and w, so this is just u plus w del a. Now we don't know what this expression is, but we know that this is going to be something like del u plus w del u del a plus del u plus w del w del a, right? And these guys now we can we can expand forward, but notice that these two things are going to be common even when you calculate del y, del b, right? So when you now go and ahead and expand del y, del b, you're going to again get del u plus w del u del b plus del u plus w del del b, right? And again, similarly, when you expand del u del a, you're going to get a bunch of common expressions, right? So let's look at what happens when we expand del u del a, right? Or let's look at del w del a maybe. So when we expand del w del a, we get okay. So del w del a is del av del a times del a. I'm just going to simplify as 1 plus del v del a times uh, yeah, basically just this thing, right? Sorry. So it's going to be yeah. So del A plus del V in some sense, right? And these two things will sort of immediately get simplified to one. This is the only thing that will remain, right? Similarly, when you compute del W del B, you'll get remember W is just a product of A and V, so you'll get del AV del B, which is del A del A del A del B plus del V del del V del B, right? Again, you'll have to expand these guys further, but these things also cancel out to one. And the fact that these things are one over here and here are something common that you can again store, right? So you keep on getting these common sub expressions. And if you notice these common sub expressions, these are essentially just the derivatives of this particular function that you have with respect to its own particular kinds of inputs, right? Okay, so let's, for a final time, let's look at a much simpler example and kind of write it all out, and this will, I think, make this what I'm trying to drive at much more clearer, right?
Yeah,
So
Diganta,
yeah.
I just got a warning that the meeting was going to end in 10 minutes. Okay. So we
Mhm.
will run the course, okay, or at least for another 5 minutes. Okay. After that,
Mhm.
we'll have to restart. Okay. Sorry about that. Yeah. You'll have
Yeah,
to
yeah, no issue.
bear with me for today. Yes.
Okay, so let's consider a very simple function. So let's say that we have some f is so let's say y is, let's say, f of g of x vector, right? And we're going to assume that g and f are vector valued function as well, right? So now, if you want to calculate derivative of y with respect to x, typically what it looks like from chain rule is that you calculate the derivative of f, and remember the derivative of f is going to be some linear function, right? And this linear function is you're going to then compose with the derivative of g, right? And this whole thing, when applied to your x vector, should give you the derivative of y at x, right? This is here as well. Notice that we can kind of reframe it in a particular way, right? So let's expand this guy out as saying that, okay, f is going to be some vector valued function, I mean vector to scalar valued function that takes, let's say, g1 x comma y, g2 x comma y, right? So then what is f prime going to be? F prime is going to be some matrix that looks something like del f del g1, right? So if I follow my convention, I should write it out as a column matrix. Del f del g1 del f del g2, and then I'm going to take g, right? So g is again takes x and y and gives me g1 g2, right? So it's going to be something that looks like, okay, it should produce del g1 del x del g1 del y del g2 del x and del g2 del y, right? And this whole thing should now be applied to my this particular vector xy, right? So this is basically what we're saying. So notice that this also you can write it out as a graph, right? So both the function application and corresponding the matrix multiplication can be thought of as a graph. How? So we can say that we're going to start with x and y, right? And then we're going to calculate g1 and g2, g1 and g2, right? And then we are going to somehow calculate f, correct? Now, notice that what we are saying here is that we are simply saying that, okay, we are going to, when we do this matrix multiplication, this f, we are taking the derivative of f with respect to g1 and g2, and then we're doing this kind of a multiplication, right? If you do this matrix multiplication, what you'll end up happening is that you're going to take this kind of a row and multiply it over here, and take this kind of a column and multiply it over here, and so on, right? That ends up looking like if you were to assign each of these edges with each one of your gradients. So you, let's say that you say that this guy gets del f del g1, this guy gets del f del g2, this guy gets, you know, del g1 del x, del g2 del x, right, on these particular edges. Notice that after doing all of these multiplications, the component that you'll get for x, right, that is going to basically be the sum of all of these products along all of these paths, right? And this is kind of the key idea behind the backpropagation algorithm, right? So you can think of it in both ways. You can think of it in terms of the computation graph, or you can think of it in terms of this kind of matrix representation. But if you're composing a bunch of functions to build a more complicated function, right, it'll essentially look something like this, or it'll essentially look something like this. Both of these are in some sense equivalent ways to think about it. And then when you want to compute the gradient, all you need to do is really just take the products along all of these paths, the sum of the products along all of these paths. And as long as you take the sum of the products along all of these paths, you should essentially be able to accumulate all the gradients that you want to, right? Okay, so now let's go back to our original example one last time, and let's see how all of this lets us build a function that, or an algorithm that will very efficiently calculate the
Okay.
gradient for us.
Diganta, we have 4 minutes left.
So I
Okay.
think at this point, yeah, let's maybe
Yeah,
switch
but
around.
the thing is, if I start a new session, I'm not sure if you'll be able to refer to the handwritten whiteboard that
Oh
you.
no, no, that's on my end. That'll remain.
Oh, that will remain. Oh, okay.
Yeah,
Okay.
yeah, yeah,
So then this might be a good point for
yeah,
us to stop and then restart. Okay. Yeah.
yeah, yeah.
Oh, yes. Thank you.